All right, AP Stat students, today we're going to be looking at section 2.1. We're stepping off into chapter 2 now. And section 2.1 is describing the location in a distribution. And chapter 2 is modeling distributions of data. Okay, so some learning objectives for this section. We want to find and interpret the percentile of an individual within a distribution of data. We want to estimate percentiles and individual values using a cumulative relative frequency graph. We want to find and interpret the standardized score, which is called a z-score, of an individual within an individual value, within a distribution of data. And we want to describe the effect of adding, subtracting, multiplying by, or dividing by a constant on the shape, center, and spread of a distribution of data. All right, so first, the percentiles. So one way we can describe a location of an individual value inside of a distribution of data is using a percentile. The pth percentile of a distribution is the value with p% of the observations less than it in that distribution. So for example, Jenny earned a score of 86 on her test. How did she perform relative to the rest of the class? Well, at 86, there are 21 scores that are less than her score. So her score was greater than 21 of the 25 observations here. You can count how many observations there are by the number of leaves here, because we got a stem and leaf plot here. So since 21 of the 25 are less than her or below her score, which is 84%, when you divide 21 by 20, you take 21 divided by 25, it comes out to be about 0.84. Should actually come out to be exactly 0.84, 0.84 there. So that's 84%. So that means that Jenny is at the 84th percentile in her class based on this test score distribution. All right, so cumulative relative frequency graph. This displays the cumulative relative frequency of each class of a frequency distribution. So we've got the age of the first 44 presidents when they were inaugurated. So there were 2 presidents that were 40 to 44, 7 that were 45 to 49, 13 that were 50 to 54, and so on and so forth there. Okay. So the relative frequency, so 2 out of 44, 7 out of 44, whatever. So you got all those. Now, cumulative frequency, notice that for the first line, it's the same, 2 out of 44, 4.5%. But on the next line, it's the cumulative frequency. So it's everybody below that amount, up to that amount, up to 49. So that this case would be 9, because 7 and 2, 9 out of 44 is 20.5%. And it continues. So the next line, you add 13 in there, so you're going to have a cumulative frequency of 22. And what you see is that cumulative frequency eventually approaches 100%, because at that point you've taken into account everything below it. You've reached 100% there. All right, z-score. A z-score is another way we can measure position in a distribution. It's a standardized score. A z-score tells us how many standard deviations from the mean an observation falls, and in what direction. If x is an observation from the distribution that has a known mean and standard deviation, then the standardized score of x is, you take that value, that particular observation value, minus the mean, divided by the standard deviation. And the standardized score is often called a z-score. So if we look at 86 right here, the class mean was 80. The standard deviation was 6.07. Okay, again, you could find those using the one variable stats on the calculator. What is her standardized score? Well, you take 86 minus 80 and divide it by 6.07, you get 0.99. So she was 0.99 standard deviations above the mean, above the class mean of 80, is what you can say, interpreting that in context. This value, the z-score, will be positive when somebody is above the mean. It'll be negative when somebody's below the mean. All right, so what happens when we transform data? When we start manipulating the data values by adding a constant, subtracting a constant, multiplying or dividing by a constant. What happens to this? So there's changes that can be made to the shape, center, and spread of the distribution. So first we'll say adding or subtracting a constant. If we add, the same number A or subtract the same number A from every observation in a set of data, then that adds A or subtracts A from the measures of center and the location, meaning the mean, the median, quartiles, and percentiles will all change by that value of A. We'll either add A or subtract A from every one of those. But it does not change the shape of the distribution or the measures of spread. You're simply shifting your entire data set up or down. You're not changing how far apart the points are, the standard deviation. You're not changing the IQR. You're adding or subtracting A from all the observations. So that is not going to change the spread. It's also not going to change the shape. You're just moving the shape of the curve or whatever it is, the graph or the stem plot or whatever kind of visual representation of it. You're just moving it up or down. All right, so examine the distribution of students' guessing errors by finding a new variable as follows. Error is going to equal guess minus 13. That is, we'll subtract 13 from each observation in the data set. Try to predict what the shape, center, and the spread of this distribution will be. So if we've got our guess here, and so the error is going to be the guess minus 13, so you can see that the mean of the guess was 16.02, the guess value. You subtract 13 from that, you get 3.02. So see, the mean just changed. We just shifted the mean down. Standard deviation did not change. The minimum, we shifted it down 13. The Q1, the median, the Q3, the max. IQR did not change. The range did not change. All right, so what if we transform it a little bit differently? Sometimes transforming converts the original observations from original units of measurement to another scale. Transformations can affect the shape, center, and the spread of a distribution. So if we multiply or divide by a constant, so if we're multiplying and dividing each observation by the same number B, that's going to multiply or divide measures of center and location. That means the mean, median, quartiles, and percentiles by that value B. It also multiplies or divides measures of spread, the range, IQR, and standard deviation by the absolute value of B. But it still does not change the shape of the distribution. The shape will still be the same. All you're doing is changing basically kind of like the scale of your measurements, the scale of your graph or whatever it is. The shape is still going to look the same. Okay, just make sure that you realize that it changes by multiplying or dividing by the absolute value of B on your range, IQR, and standard deviation. Okay, because B can be negative technically. And you would multiply or divide all the measures of center and location by B, even if it's negative. But it's the absolute value of B you're multiplying or dividing by when you're talking about measures of spread. All right, so because of our group of Australian students is having some difficulty with the metric system, it may not be helpful to tell them that their guesses tended to be about 2 to 3 meters too high. Let's convert the error data to feet before we report back to them. They are roughly 3.28 feet in a meter. So you basically could convert, changing your units. If all your observations are in meters, you can change them to feet or back and forth or whatever, depending on what you're looking at. So the mean in this case of the error was 3.02. We're going to multiply that by 3.28 and get 9.91 for our new mean. Standard deviation also gets multiplied by that. And you can see how the data here is transformed based on that previous slide there. All right, so those are our objectives for this one, and you're going to have some problems to do with this set.